All right, students, hello. Here's my first record lecture for you guys. Go ahead and get out a piece of paper, whether it's lined paper or printed paper, I don't care. And then maybe a couple different colors to write with. You know, I like to keep things colorful to make your notes interesting. But during this video, you do need to take notes. If you don't take notes, this video will be pointless to you. So you need to write down everything I'm writing down and keep it in your chemistry binder so that you can refer back to it. So today we're going to go over the ideal gas law, which is the last gas law equation that I'm going to go over with you guys before we move on to gas stoichiometry. Even though I'm not here in front of your face telling you what to do, I am just here virtually. You still are going to be held accountable for knowing this information. And this lecture is just the same as I would do it in the classroom. So you need to make sure that you're learning, paying attention, and you can message me if you have any questions about it, okay? So here's the gas law equation we're going to learn. It's PV equals nRT. Okay, so that's the equation, PV equals nRT. So let's talk about what each of these variables stand for. Now, some people call this the Pivnert equation because that's kind of what it spells out. Not to be confused with pervert, Pivnert. Okay, a lot of kids say it wrong and then it creates all sorts of problems. So PV equals nRT. All right, this is the equation. And if you want to put a little highlighted box around it, it's really obvious in your notes. Not a bad idea. So let's talk about each variable. The first one is P. P stands for pressure, right? And when we're using this equation, we're going to want to make sure our pressure is in atmospheres. Okay, and I'll explain why here in a second. Next one is V, which is, of course, volume. Volume. And in this equation, we want to make sure our volume is in liters. Okay, so in this particular equation, it does matter that your volume's in liters. In the other equations we've already gone over, if it's in milliliters, as long as it's the same on both sides, it doesn't matter, but in this equation, it needs to be in liters, okay? N, if you remember, stands for number of moles, so that's just moles. R, let me skip over it for a second, I'll come back to it. T is temperature, right? And whenever we're dealing with gases, our temperature always needs to be in Kelvin, right? Okay, so now let's come back to R. R is new, we've never seen this before. R is what we call our ideal gas constant, and its value is always going to be the same, okay? It's a constant, so it's 0.0821. It's always going to be that number, and the units are kind of funky. It's liters times atmospheres over moles times Kelvin, okay? So that whole thing, is the units for this number, okay? The units are like big. Okay, so those are the units for your R value. That's important, okay? Now you guys know that in the past week or two I've been assigning you guys videos from Tyler DeWitt. He's like my YouTube homie. Not really, I don't know him, but I really like his videos because I think he does a really good job explaining things. So if you were to watch his video on ideal gas laws, he also goes over that there are other values for R. So keep that in mind if you're Googling stuff or looking for help on the internet. There are different values that exist for R, but we are going to use the one that has atmospheres in it just to stay consistent. So you guys, hopefully that simplifies it for you. So you only have one number to remember. And as long as your pressure is in atmospheres, you can use this R value every time, okay? So if you get a problem where your pressure is not in atmospheres, convert it to atmospheres, and then you can just use this one. And so in case we've forgotten how to convert these things, let's write our conversion factors over here to the right. So let's remember that, I'm going to write a few things here, that 1 atmosphere is equal to 760 torr, which is equal to 760 millimeters of mercury. Remember, a millimeter of mercury and torr, those are the same thing. And it's also equal to 101.3 kPa. That's kilopascals. Okay, so those are our conversion factors for pressure. For temperature, remember that if we want to go from Celsius to Kelvin, we know that Kelvin is what you have to do is you take whatever it is in Celsius and you add 273, right? So that's how we convert to Kelvin. And then the last thing to remember is that 1 liter is equal to 1,000 milliliters, right? So we want to remember those things in case we need to do some conversions to get into these desired units here, okay? So let's go ahead and do an example together now that we have that all set up. So let's do example 1. Example 1. Boop. All right. So if you want to pause the video and write this down, more power to you. If you don't want to do that, that's fine too, but you do need to write down all the work so you can refer back to it. Okay, so example 1 says at what temperature in Celsius will 0.780 moles of neon gas occupy 4.3 liters at 1.75 atmospheres? So let's write down what we know. So we know our equation is going to be PV equals nRT, and let's write down each variable. Okay, get it all laid out like that. Okay, so pressure. Let's see, which of these numbers is pressure? Looks like this one, because this one's in atmospheres, and atmospheres is a unit for pressure. So under pressure, for P for pressure, let's do 1.75 atm. Okay, volume. Let's see which of these is volume. Well, here we have 4.30 liters. Okay, so liters is a volume unit, so let's go ahead and 4.30 liters. Write that down for volume. N is number of moles, so it says right here we have 0.780 moles, so let's write that down. R, I told you R is always going to be this, so let's write that down. R is 0.0821 liters times atmospheres, moles times Kelvin. I know it's annoying to write that down, but get over it. Okay, and temperature is what we're looking for. We're looking for temperature, and even though it says in Celsius, whatever we get is going to be in Kelvin, and then we're going to have to convert back to Celsius by subtracting 273, okay? So now let's plug everything into our equation. I'm going to use not a Sharpie because it takes up too much space. So I'm going to use this red pen. Let's plug everything in that we know. So P is 1.75 atmospheres. Let's plug in V. V is 4.30 liters. Equals N, which is 0.780 moles, times R, which I told you is 0.0821 liters times atmospheres. I know it's tedious to write out the units, but there is kind of a method to my madness, and I'll show you why here in a second. And then T is our variable, so I'll just write it as T. That's my unknown variable. So now we need to isolate that variable. And the way to isolate the variable, since these are all being multiplied by each other, we're going to do the opposite of multiplication, which is division. So let's divide by the things next to the variable so that they cancel out. Okay, so this one, divide by that so it'll cancel. Same thing here. And I'm going to write it kind of tiny, but it's there. Cancel. Same thing to the other side. So whatever you do to one side, you have to do the other. So because we divided by these things on this side, we need to divide by these things on this side as well. Okay? Liters times atmospheres over moles times Kelvin. It's kind of smashed, but there it is. Okay? Okay. So now I'm ready to get my calculator. These ones are canceled. My variable's isolated, so now I need to do all this math in my calculator. So, oopsie. I'm going to go ahead and do 1.75 times 4.30 divided by, and then I'm going to put in parentheses 0.78 times 0.0821. Close my parentheses. If you don't want to put parentheses, it'll probably come out wrong. And you should get 117.5, blah, 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 blah. Okay? So my T, or for my temperature, is going to be 117.50, 835, etc. All right, let's see how many sig figs we need. It looks like we need 3 sig figs. So let's round that to 118 because we look at the 4th sig fig over. If it's 5 or above, it's going to bump it up. Okay, so 118. And then our units are going to be Kelvin. Okay, and there's a couple reasons why. First of all, whenever we're doing gas law stuff and we solve for temperature, it's always going to come out in Kelvin. Second of all, if we look at all these units we wrote out, atmospheres cancels with the atmospheres in our R value. Liters cancels with the liters in our R value. Moles cancels with the moles in our R value. And what is left? It's kind of hard to see, but it's right there. A little K for Kelvin. So that's what our units are going to be. Now, if you look at this question, it says, what's the temperature in Celsius? So we need to convert this back to Celsius. And the way we do that is by subtracting 273. So I'm going to do 118 minus 273. And I get negative 155 degrees Celsius. Okay. And that's what I get for my answer. And that is correct. Okay. Okay. So that's how you use the gas law. It's basic algebra, just like you guys have been doing. The only thing that's kind of new is this number, but as long as you plug this number in for R every time, you should be in good shape. Let's do one more example together, and then I'll set you loose. I'm going to try to keep this video somewhat short. So one more example. So let's do example number 2. Flip your paper over. Example 2. All right. So example 2. We are going to use our PV equals nRT equation. So let's write down everything we know, all of our variables. Okay, so it says when 0.250 moles of a gas, okay, well, that is, I'm going to use my blue because it's kind of not as huge. So that's moles. So moles goes under N for number of moles. So 0.250 moles. It's placed in a container at 25 degrees Celsius. So that's my temperature. So 25 degrees Celsius, but we know that needs to be in Kelvin, right? So let's add 273. And that should give us, I think, 298, right? 273 plus 25, 298. So that will give us 298 Kelvin. All right, and then it says it exerts a pressure of 700 millimeters of mercury. Okay, so 700 millimeters of mercury, that needs to be in atmospheres, right? And if you remember on the front of our notes, we just said here that 1 atmosphere is equal to 760 millimeters of mercury. So let's do a little conversion here, because we have millimeters of mercury here, we need millimeters of mercury here, and we're looking for atmospheres, so that goes on top. And we know that 1 atmosphere is equal to 760 millimeters of mercury. So when we put that in our calculator, we're going to do 700 divided by our 760, and that's what we get in atmospheres. So it's going to be, let's see here. Let's do, because this technically had a little thing there, let's do 3 sig figs. So 0.921 atmospheres. Okay, so that's what we'll plug in for our pressure. Because remember, pressure needs to be in atmospheres when we're using the ideal gas law. So 0.921 atmospheres. Okay, it says what's the volume of the container. So the volume is what we're looking for. And R, we know, because I told you that R is always going to be this number here. So let's write that down. 0.0821 liters times atmospheres over moles times Kelvin. Okay, so your units that are inside your R value should match your units that are in your other variables so that they'll cancel out. Okay, so let's plug everything in to our equation. Okay, so P, let's see here, 0.921. So P times V is my unknown, equals N, which is my moles, times R, which is my 0.0821, liters times atmospheres over moles times Kelvin. I know, it's annoying to write out. I'm right there with you. And then our temperature has to be the Kelvin value. Okay, this is the one we got to use. So the 298 Kelvin. Okay, so our variable that we are trying to solve for, our unknown variable here, is volume, right? It's volume. So let's divide by this to get rid of it on this side so that our variable can be isolated. So 0.921 atmospheres, divide, do the same thing to the other side. Okay, so now our variable's isolated. Let's figure out what volume is. So I'm going to do my 0.250 times 0.0821 times 298 equals divided by 0.921, and I get 6. Oh, can you guys see that? 6.64 blah 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 blah. Okay, so that's what you should have gotten. 6.641096 dot 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 dot. Okay, and let's see here. Because this is volume, it should come out in liters. Let's double check that everything canceled. Moles canceled here. Yep. Kelvin canceled here. Yep. Atmospheres canceled here. Yep. And I'm left with liters. Woohoo! So I must have done it right. Okay. Now I need, let's see, let's do 2 sig figs because technically the 25 only had 2. And I like to look at the original numbers. So if we're doing 2 sig figs, this would be 6.6. 6.6 liters. And that would be my answer. Woohoo! All right, so there are 2 examples for you to help you know how to work out these problems. You should be in good shape. Message me if you have questions or you're not sure about something, and hopefully I can help you out. Bye.